Okay, now we're going to just talk about fission and fusion in relation to some of the stuff we've done on binding energy. So a little bit of a quick reminder. First up, the mass of an object increases or decreases when it gains or loses energy. This is from E equals mc squared, and we think of it as energy being another form of mass, or mass being another form of energy. The mass of the nucleus is less than the mass of the nucleons. We showed that, so therefore energy is released when the nucleus is formed. This is called binding energy, and to make it more of a useful comparison, if we average it out or divide it by the number of nucleons, then you have the binding energy per nucleon, which is a direct measure of stability. So what we're going to look at today, we're going to look at fission and fusion to see the energy released in both of these processes. Quick overview of fission then. It was done in 1938, uranium-235. If you bombard it with neutrons, it splits into two fragments. The fragments that it splits into, it isn't predictable, but there's a few different variations. I've listed out two that are here. So here uranium's gone into cesium and rubidium, and here the uranium went into barium and krypton. Now with these you also get neutrons coming out. And this is useful because this gives us the idea of a chain reaction. So this little animation here, if we just watch it and click through, the neutron's absorbed by the uranium nucleus, it becomes unstable, it splits into two smaller fragments along with two or maybe three neutrons. Then these neutrons can go on to split further nuclei of uranium, which then go on to split and produce more neutrons, and these neutrons were now on 3 plus 3 plus 3, we're on 9, and then these can go on to split another 9 uranium nuclei, and etc, etc. So you can see how a chain reaction is formed, releasing a lot of energy, because each of these processes releases energy. And that's what we're going to calculate now. So can we calculate how much energy will be released per fission? Okay, so we'll do some work on our binding energy like we've been doing. One possible fission is uranium, which we've got the mass. The new nuclei are unpredictable, but as a possible example, as we said, was rubidium and cesium. Here's the two masses. Two more neutrons are also released. So let's just do the equation. So complete the equation for this fission reaction. We've got it here. So a neutron is absorbed by uranium, produces rubidium, cesium, a neutron. Be prepared to be able to complete those for the exam. Calculate the mass lost and therefore the energy released in this process. So let's have a look here. We've got 235, which is the uranium, plus the neutron, minus these are the two nuclei that it splits into, and we mustn't forget to take into account the two neutrons. So if you put all that into a calculator, you end up with a mass lost of 0.18318 U, which is 170 mega electron volts if you just convert that, and I'm converting it again into joules. So that's 2.72 times 10 to the minus 11 joules. Just be worth you checking that and make sure you can do it. So calculate the number of such reactions needed per second to produce a power output of 1000 megawatts. So we're just here considering the nuclear power station with a power output of 1000 megawatts. So 1000 megawatts is 1000 times 10 to the 6. Divide that by each of our fissions, which we worked out was 2.72 times 10 to the minus 11 joules, and this will give us 3.66 times 10 to the 19 fissions per second. Remember, 1000 megawatts means 1000 megajoules per second. So dividing that by the number of joules per fission gives us 3.66 times 10 to the 19. So now we could work out how much mass do we need to run this reactor if we've got that many fissions per second. So the number of fissions per second times the mass of a uranium nucleus in kilograms. Well, we know that's 3.66 times 10 to the 19, just worked out. This is the mass in U. Convert it to kilograms by multiplying by 1.661 times 10 to the minus 27, which gives us an amount of fuel of 1.44 times 10 to the minus 5 kilograms per second. And then if we just factor that up with 60, 60, 24, 365.25, I've done 365 and a quarter days in a year, gives us 452 kilograms per year. So some of the work you've done earlier in your school, where you consider the amount of coal a coal-fired power station uses, is quite scary. It's numbers of train loads per day. Here we've worked out you can run a 1000 megawatt reactor with about 450 kilograms of fuel in a year. Okay, let's look at binding energy and fission. excuse me, in fission, both fragments repel each other to overcome the strong nuclear force. Hence the split. There's a release of kinetic energy. This is where the mass goes. Remember, we have to account for it. So mass is converted to energy, and the energy expresses itself in kinetic. The two fragments are smaller. They're more tightly bound than the original, so that therefore they have a higher binding energy. They are more stable, and the kinetic energy released is equal to the change in the binding energy. So binding energy per nucleon for uranium is 7.6. You can work these out or use the information that we've done before. So 7.6 times 235 will give us, remember, 235 nucleons in a nucleus. So this gives us 1786 for the whole nucleus, because this was per nucleon. Barium is 8.27, so again 144 times that. 144 nucleons gives us that for barium, and krypton 90 is 8.6. So you can see here, look, 7.6. The two products have got a higher binding energy than the uranium. This gives us 774 for the whole nucleus. So now we can do some sort of accounting. We can say to split uranium up, you have to put in 1786. So if we start off at 0, and then if we physically had to split the uranium nucleus, we'd be minus 1786 mega electron volts. But then when barium nucleus forms, we get out 1191. So minus 1786 plus 1191, we're now at minus 595. So we're still negative. We're still in negative energy, but we've still got to put together the krypton nucleus. And when we do that, we get 774 out. So minus 595 plus 774 now gives us a positive amount of energy, 179 mega electron volts. So you can see that you get energy out when you split uranium up and make two other nuclei. So 179 mega electron volts is released, and this is similar to the calculation that we just did, and without using binding energy, but talking about the mass lost. Okay, and just link this back to last lesson. Here's our binding energy per nucleon plot. So here's uranium in this area, and you can see, as we mentioned last time, we're going up this part of the graph. So as we split this uranium and make two products that are going to be in this area, we end up with an energy output. Okay, let's have another quick look at the process of fusion. Only takes place if nuclei combining and colliding at high speeds. We need to overcome the Coulomb repulsion and allow the strong nuclear force to pull them together as they get close enough. This is the idea of nuclear fusion is this, and this is an experimental fusion reactor you might have looked at. This looks a little bit like the one we've got down in Oxford at the Jet Laboratories. If we go and have a look through, we can see what happens inside. It's a simple animation. This would be tritium deuterium, and if we get them moving fast enough, give them enough kinetic energy, they can get close enough so the strong nuclear force pulls them together and they form helium with a spare neutron. Now, this is what we would try and do in a fusion reactor on Earth. This is what happens in stars like our Sun. So you can see there's a few fusion reactions that lead us to a fusion of helium and helium eventually. But we've got protons to cause hydrogen. We've then got hydrogen and another proton giving us helium. And all of this releases energy in the process. This is the reaction that we have done on Earth. We've done this. We haven't kept it going yet, though. We can sort of do it for a few seconds, but the idea is to try and keep this going to get a net energy output using fusion reactors. So we've got to calculate the energy released. We're going to again think about using E equals mc squared, but throughout this we need to remember this is experimental on Earth. They're still in development, and the reason being that we do find it difficult to reach the temperatures required. It takes a lot of energy to reach the temperatures involving superconductors and superconducting magnets, and so we end up putting more energy in than we get out. So let's just do some calculations. We'll base it on the Sun. We've got some information up here. So one nuclear fusion process is the fusing of two deuterium nuclei. Calculate the energy released when two deuteriums are fused together to form a helium-4 nucleus. Okay, so here we go. This is the two deuteriums. So 2 times 2.01410 minus 4.00260, which is the helium, and we end up with an amount of energy of 0.0256 So let's just convert that into kilograms, amount of mass, sorry. Let's just convert that into kilograms, and then we'll convert that into energy using mc squared. And remember, I could have just done the conversion of 1U equals about 930. Here I've done it the long way around as well. So I've got about 24 mega electron volts per fusion. So calculate the number of such fusions per second needed to produce the sun's output power of 4 times 10 to the 26 watts. So we're suggesting that so many fusions, an unknown number of fusions, each at 3.83 times 10 to the minus 12 joules equals 4 times 10 to the 26. And remember, that's in watts, so that's joules per second. Just dividing this through, you can get an answer of N being equal to 1 times 10 to the 38 fusions per second. Okay, so if you just do 4 times 10 to the 26 divided by 3.83 times 10 to the minus 12, and we get that many fusions per second. So what mass of hydrogen would this be? Well, if we need 10 to the 38 fusions per second, each of the hydrogen, we need 2 of the 2.01410s up here, and then we need to convert that into kilograms. So doing all that, you get an answer of 7 times 10 to the 11 kilograms of hydrogen per second. It's worth stopping for a moment just to think that the sun, our sun, is getting through that amount of hydrogen per second, which is quite gobsmacking. Estimate the lifespan of the sun given that it has a mass of about 2 times 10 to the 30 kilograms. So this puts it into perspective. Even though we're getting through that amount of hydrogen, we've got a mass of 2 times 10 to the 30. So 2 times 10 to the 30 divided by 7 times 10 to the 11. Rough calculation, the sun's going to last about this many seconds, 2.8 times 10 to the 18. So let's just convert that into years. So divided it through and we get 100 billion years. Now, from whatever you know about the sun, you possibly now at this point thinking that's too long. The sun, estimated life of the sun is it's about halfway through, and it's currently about 5 to 6 billion years old. So this isn't very realistic. Obviously, not every single hydrogen nucleus will be able to fuse, so the life isn't going to be anywhere near as long as this, as we said, somewhere between 5 to 7 billion years. And just to link this back to the binding energy, so the binding energy per nucleon plot, remember with hydrogen and helium we're going up here, and even sometimes to helium-4, which is a big energy difference, you can see. So it's in the other side of the graph where we're going up to a more stable. Okay, let's just do a comparison of energy released in fission and fusion. Fusion releases energy, and in the example in the sun it was about 24 mega electron volts is released when 2 hydrogen nuclei fuse, and this corresponds to about 6 mega electron volts per nucleon, so 24 for 2 hydrogen, so divide that by 4, because remember there's 2 nucleons in each hydrogen. Fission of uranium to barium and krypton produced about 170 mega electron volts per fission. So again, dividing this through, this is about 0.7 mega electron volts per nucleon. So we've got two numbers. There's more energy released per fission. So here we've got fission is 0.7 mega electron volts per nucleon, and fusion is 6 per nucleon, but there's more energy released per fission than per fusion, because here, you know, it's 170 mega electron volts per fission as opposed to 24 mega electron volts per fusion. But we need to think about the energy released in an amount of fuel. So even though fission releases more energy per event than fusion, you could say, let's just think about the energy released in 1 kilogram of fuel, of fission or fusion material. Fusion definitely wins at this point, and how do we know that? Well, there'll be a lot more fusions possible in 1 kilogram of material. If you think that 1 fission of uranium is going to use quite a lot of mass, it's going to use more mass than 1 particular fusion. So let's just see if we can do this calculation. The energy from fissioning 1 kilogram of uranium-235, well, 235 grams of uranium contains 6 times 10 to the 23 atoms. So if we just factor this up, 1 kilogram is going to give us 2.6 times 10 to the 24 atoms. Now each of these are going to give us 170 meg. So if we split up all of those atoms, each with a nucleus, then we're going to get that many times 170 mega electron volts, which will give us 4.34 times 10 to the 32 electron volts. But now let's do the same idea from fusing. If we fuse 1 kilogram of hydrogen, 6 times 10 to the 23 atoms is only 2 grams, so 1 kilogram of hydrogen is going to give us 3 times 10 to the 26 atoms or nuclei to fuse. So let's do each of those. 3 times 10 to the 26 times by the amount we get out from one fusion, but here we've got to divide it by 2, because remember we need 2 nuclei to fuse, and we get there 3.6 times 10 to the 33 electron volts. So we've got a larger amount of energy here, 3.6 times 10 to the 33, than we did here, 4.34 times 10 to the 32, when we consider fusing or fissioning 1 kilogram of fuel. And this is why fusion for the future certainly will be revolutionary and will change the way that we make our energy.